So, hello everyone, I welcome you all again to the fourth lecture part 2 of electromagnetic induction. In the last lecture at the last point we talked about a little discussion was been told on eddy currents. What are these eddy currents? Why is this being induced? A simple concept of pendulum was been told to you. So, course outline before that we started with electromagnetic induction's definition, then the experiments of Faraday and Henry. There were 3 experiments 1, 2 and 3, followed by the magnetic flux phi b value which is equal to B dot A, it is a dot vector product. Moving on to the Faraday's law of induction, that is epsilon which is equal to minus n d phi b by dt. Moving on to the Lenz's law and conservation of energy. Moving on to the motional electromotive force, if the rectangular conductor is being used and a PQ conductor is moving towards the magnetic field with a constant velocity v, then epsilon is equal to B L V, the magnitude will be equal to B L V. Then the next point is eddy currents. Before eddy currents we talked about a simple problem which was involving Joule's heat, that is conversion of mechanical energy into electrical energy and then electrical energy into thermal energy. So, the thermal energy involved also talked about why is it happening and a problem associated with conversion of electrical energies and Joule heat concept was being dealt with. Now, before starting the concept of inductance and AC generators, eddy current concept is being very important and hence we are talking about eddy currents. So, in last lecture I started with a simple experiment of eddy currents in which a pendulum was being involved which had a copper plate, and this copper plate moved inside and outside the magnetic field produced due to 2 bar magnets. These 2 bar magnets are being depicted here in your slides. This is this is a bar magnet and this is also a bar magnet. So, now let us move on to the discussion forward. So, the last point which we stopped at was ki the after a particular time t, the pendulum reached a halt position. Why was this halt position being reached? Because there is a electromotive force happening away into the direction of the pendulum. If it is going inside the magnetic field B, the force tries to resist its motion. When it is going above, it is try to resist its motion again. When it is coming down, it tries to resist its motion again, and due to this the frequency of the pendulum keeps on decreasing and finally it comes to a stop. So, moving on to the next concept, please let me iterate to you. So, if rectangular slots are made in the copper plate as shown in the figure. So, what does rectangular slots mean is in the first concept. So, what does rectangular slots mean? The comprising area is being reduced by a little amount by making these grooves, by deleting this area. So, these things are nothing but rectangular slots. So, if rectangular slots are made in the copper plate as shown in the figure, this is here it is also shown for a more clear view. The area available to the flow of eddy currents is less, as it is quite evident that if the area is being decreased, the area is being removed from this position. Area is being removed from this position and therefore, area is less. If the area is less, then the magnetic flux which will be derived or which we will get, which the copper pendulum will get when it will try to come in the magnetic field through its movement will decrease, because there is a small area because due to a little less change in area. Due to a little less change in area, there will be a less electromotive force involved or dealt with, which will try to oppose the reaction, and hence there will be a more time taken for its halt position. So, this is the only concept being told here. If rectangular slots are made in the copper plate as shown in the figure, the area available to the flow of eddy currents is less. Thus, the pendulum plate with holes or slots reduce electromagnetic damping. Why it is told as electromagnetic damping? Because the damping involves electromagnetic induction and this plate swings more freely. So, it is quite evident that the swinging will be more because the force or the resistive force will be quite less. So, these 2 points are being dealt with. Next, note that magnetic moments of the induced current which oppose the motion depend upon the area enclosed by the currents, as it is quite evident that phi b is equal to b dot a, that is a dot vector product which is equal to b into a into cos theta. Therefore, phi b is a function of area A. So, if the area A is being reduced, that directly means that the value of phi b is also reduced, or if delta phi b, so delta phi b is a function of delta A as long as b and theta are constant. So, if the change in area A is less, that means change in phi b will be less. What does change in area depict here? Here change in area depict is the amount of area which is under the influence of magnetic field B. It does not mean that the area of the rectangular slot complete area will be considered here. No, complete area will not be considered here. It is only that area which will be under the influence of the magnetic field B. So, note that the magnetic moments of the induced current which oppose the motion depend upon the area enclosed by the currents. This fact is helpful in reducing eddy currents in the metallic cores of transformers, electric motors and other such devices in which a coil is to be wound over a metallic core. So, that is why there is a reduction that is why anything which is involved in induction of currents in these all transformers, AC generators and so on involves slots, involves grooves. Why there is an involvement of these slots or grooves? So as to reduce eddy currents. Why there is a need to reduce eddy currents? So that there is less dissipation of energy and more energy is being evolved, that is means more, what we can say, more good energy. What does I mean by good energy? Is any energy which is useful for us, and any energy which is not useful is dissipated. So, bad energy gets less and good energy gets more. So, that is why eddy currents are being involved, because anything bad as in here means that it is joule energy, that is heating loss. We require our energy to be more and more of good part, that is if it is required for any let us say electrical consumption or electrical energy is required, we do not require the energy to be dealt in joule heating loss only. If majority of 90% of thing is evolved or it is induced goes into heating loss, and it is of no use to us, it is wastage only. That is why eddy currents have to be reduced for more and more generation, for more and more good energy generation. So, hence this concept is very important for inductance and transformers. So, moving on to next point, that eddy currents are undesirable. See, next point is that only, that eddy currents are undesirable. Why they are undesirable? Since they heat up the core and dissipate electrical energy in the form of heat. We already know that anything which when it gets heated up, it leads to either voltage or it does not work. In normal day to day scenario also, in our day to day scenarios when we use coolers in summers, if the motor gets heated up, it does not get work and hence we have to replace it. The final form is replacing only. So, if in big transformers these replacement is very hard, it takes time, it takes manpower, it takes money. So, to reduce these all things, to increase our productivity, we use slots and grooves in our cores. Moving on to the next point, eddy currents are minimized by using laminations of metals to make a metallic core. So, sometimes laminations are also used to make a to reduce eddy currents. The laminations are separated by insulated material like lacquer. This is just an information part. Since the dissipation of electrical energy into heat depends on the square of the strength of electric current, as we already know that Pj, let me write it above. So, Pj is equal to I square R, that means Pj is a function of I square. I square is nothing but squared I. So, since the dissipation of electrical energy into heat depends on the square of the strength of the electric current, heat loss is substantially reduced. So, as it is a squared function, so reduction of even 2 values leads to a reduction of 4 units in heating loss. That is why any reduction in current, any reduction a very minute or let us say, let us go into this part, that a very minute reduction also can play a major role in the reduction of this Joule heating loss. And if the value gets increased, if by any chance we try to reduce this electric current, eddy currents very more, then it is very beneficial for us. So, this is only the concluding statement of this slide, that if you try to reduce the eddy currents, then it is very good, and hence good energy is more and bad energy is less. Moving on to some of the applications of eddy currents. So, eddy currents are used to advantage in certain applications like magnetic braking in trains. What is magnetic braking in trains? You can understand from this figure also. So, strong electromagnets are situated above the rails in some electrically powered trains. Any trains which are powered by electric are known as electrically powered trains. So, as you can see, electromagnets are being kept here. These are electromagnets. So, now what is happening is, please try to understand, it is a very good phenomena. So, now when the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. So, because there is already a magnetic field acting upon the rails near the rail position. So, now what is the use of the braking system? We need to apply brakes, or we need to stop the train in a very limited time, in a very small time. So, what happens is, when the electromagnets are activated, as we already know, in an ideal case, if we are going to the real life scenario, anything which involves electromagnets, anything which involves magnetic field B, anything which involves related to concept or phenomena of electromagnetic induction will lead to induction or will lead to production of eddy currents. What will eddy currents do? They just try to oppose our force, and if the value of these eddy currents are very large, as we already know that the value of eddy currents large is directly proportional to I square value. So, what will it do is, it try to oppose the force, and that is only required for to stop the train. So, what happens is, when the electromagnets are activated, the eddy currents induced in the rail oppose the motion of the train. So, if this is the direction of train involved, so then the eddy currents, as you can already see, this is the direction of eddy currents. If you can see clearly, the direction of eddy currents is in clockwise sense. That means the induction of force will be opposite. We have already learned this concept when we are talking about motional electromotive force also, that it will try to oppose the force of the induced electric current, and hence there will be a direction. In this direction the braking force will act, and hence the braking of the trains will happen. So, by using a simple electromagnet inside or near the wheels of the train, eddy currents will lead to friction, and hence it will stop the train. As there are no mechanical linkages, the braking effect is smooth. No mechanical linkages, as in this is not directly connected by any mechanical sense. This is not connected by mechanical sense. Only this concept is being told here. Next thing is electromagnetic damping. Electromagnetic damping is nothing but if we try to reduce any movement which is going in some, what we can say, for example, we can understand the situation is, electromagnetic damping can be used for any movement which is using a frequency part. Let us say a pendulum, a very strong pendulum, a very strong gear is moving. So, to reduce it or to reduce the damping position, the application is being dealt here in electromagnetic damping. Eddy currents are being involved in electromagnetic damping. So, certain galvanometers, we know what is a galvanometer. Galvanometer is denoted by G. It is used to know if the current is passing through a circuit. So, certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates as in this direction, like this or like this, either the movement can be in this direction, the movement can be in this direction, the movement can be this also. A vibration, a small vibration can also be a damping. So, when the coil oscillates, the eddy current generated in the core oppose the motion and bring the coil to rest quickly. So, this is a simple a more advanced version of this concept only. This concept only is being talked about in that application. Moving on to the third application, that is induction furnace. As the name suggests, induction furnace. So, what does induction means? Anything which implies or which uses the concept of induction. What is a furnace? Anything, any material which is used to heat up. Any heating application is being dealt in the use of what? Furnace. So, induction furnace is anything due to which a heating application is being procured, which also involves induction, is known as an induction furnace. So, now induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. So, if the high temperature are being dealt with, then we can use it to prepare alloys also. This is a simple not a simple, it is a typical figure of induction furnace. So, as you can already see, so there is an electric current being applied here, it goes in coils, like this. Due to the more version of coils, there is an induced EMF. Due to an induced EMF, there is an induced EMF, there is a production of eddy currents. Due to this eddy currents, joule heating comes into picture, and due to this joule heating comes into picture, the temperature increases and hence a furnace is being created. So, this is a heating coil here, the magnetic flux can be seen like this, eddy currents are moving in this direction. So, due to this heating induction furnace, application of eddy currents are being dealt with here. Moving on, a high frequency alternating current, just a simple brief of the procedure involved in induction furnace. A high frequency alternating current is passed through a coil which surrounds the metals to be melted. So, if this is the metal, to be melted, then a high frequency alternating current, AC current, is passed through a coil which surrounds the metals to be melted. The eddy currents generated in the metals produce high temperatures sufficient to melt it. So, as we already know, it is nothing but Joule heating loss only, the Pj is equal to I square R. As eddy current increases drastically, Pj increases drastically. Moving on to electric power meters. Electric power meters are nothing but every household has a power meter installed. Its value increases and hence we pay our bill. So, electricity bill is directly linked to electric power meters only. Everyone has these electric power meters in their households, even you have this in your household. So, this is a simple concept, this is a simple example in our day to day life, in our household life, which involves the application of eddy currents. So, what is an electric power meter? A shiny metal disc in the electric power meter rotates due to the eddy currents. So, if I tell you like this, there is a number written here, let us say 0, 1, 2, 3, 4. So, behind this there is a metal disc which keeps on rotating. So, this rotates like this, then 5 comes, it rotates like this, then 6 comes, and after this the electrician or anyone who needs to measure your electric meter, they come after 30 days, they measure and hence you pay the bill. The shiny metal disc in the electric power meter analog type rotates due to the eddy currents. So, this rotation is due to the eddy currents. Electric currents means eddy, so the calibration is being like this, that the eddy currents are being, so let us say for example, ki if there is a 5 ampere of eddy current, then it will change it to 1 unit, you change it by 1 unit. I am just telling an example, exact value is not being known. So, something like this is dealt apart in the actual electric power meter. Next, electric currents are induced in the disc by magnetic fields produced by sinusoidally varying currents in a coil. So, this is a typical example, please do not get feared up by this diagram, it is not of much use, but just to explain what is the electric power meter, I explained this using the photo here. So, electric currents are induced in the disc. So, here an induction is done, a pressure coil is being used and this recording mechanism is being used. This is the disc, it keeps on rotating and hence the numbers are being visible. You can observe the rotating shiny disc in the power meter of your house. This is the point I already told you. So, after electric power meters, let me conclude this 4th lecture part 2 also. So, in this we learnt about what is eddy currents, why is it required, why do we need to minimize these eddy currents, Now, more application part about this will be dealt in inductance and AC generators, but for now we learnt many examples of eddy current applications like the braking system in trains, also inductance furnace and so on. So, this was fourth lecture, and just the course progress is that electromotive force is being dealt, and in the subsequent lectures we will go with inductance and AC generators. So, thank you.